Hello, everyone, and thank you for joining us on this episode of Nature and Science Podcast. I'm your host, Don Murphy. Joining us today on this episode is Dr. Craig Hane to talk all about math. We will explore what math is. We'll discuss the definition of an axiom or postulate, which serve as the foundation of mathematics. We'll also take a look at some of the unsolved problems of math and explore the minds of the greatest mathematicians of all time. Dr. Craig Hane is on a mission to revolutionize math education and empower individuals with practical tools to unlock their potential. With a Ph.D. in algebraic number theory, decades of teaching experience, and a passion for breaking barriers, Dr. Dell offers a compelling mix of expertise, innovation, and storytelling that resonates with listeners of all backgrounds. Craig, welcome to the program. It's good to have you with us today.
Thank you, Don. My pleasure.
Sure. So why do you love math, Craig? What got you started? I think I read somewhere that you had an uncle that turned you on to math when you were young.
Yes, my Uncle Davis was a barber and a builder, and he knew practical math for building. He wasn't a math teacher. And when I
Mhm.
was 5 years old, the first thing he did is he taught me to count. Used Cheerios till we got up to 10. Then he started using pennies and dimes. And when I was 5 years old, I learned to count. And when I went to school at age 5, public school, in a small school in Indiana, I was the only student that had been taught to count. And so my teacher enlisted my aid in teaching my fellow students how to count. And that gave me a lot of self-esteem. I was the youngest kid in my class. I couldn't sing. I can't color. I'm colorblind. I couldn't skip, but I could count. And that got me started. And then he taught me practical math. And so I always knew math that most of my teachers didn't know. And I would tell them what my Uncle Jack had taught me, and I
Right.
could apply it. And I loved math that way. And then just kept learning math and applying math. I love to learn math, and I love to apply it, and I love to teach it.
So if I'm a young kid sitting at your knee wanting to learn, and the first question I ask you is, Craig or Dr. Hane, if I'm a
Well,
respectful kid, uh, what
Papa.
is math? What is math? What would you tell me?
Well, math is a sort of a language. I call it God's language. And you learn a natural language. Like if you're in America, you learn English or
Mhm.
Spanish. If you're in China, you learn Chinese. But math is a universal language that's the same everywhere. And it involves concepts and symbols that let you communicate things that you can't communicate with a natural language. So
Mhm.
for example, numbers, 1, 2, 3, 4, 5, that's the first thing you learn usually is just how to count. And we have a wonderful decimal number system that our ancestors invented that let us count as high as you want to go. And that's the first thing that I teach at class. Then you have geometry. How long is something? What's the area? What's the volume? And you need that for all sorts of technical subjects. And math is a way you can do that you can't do it with a natural language very easily, but with math terminology and concepts, you can do those kind of problems.
I understand. So, what's an example of that? You mentioned area for example, and I remember so clearly when I was a kid, the first time I had geometry, and the first thing in geometry we learned was about area. And so we had a square, and the teacher said, inside this square is an area.
Mhm.
And we sort of use math to do that. And so, what's that all about? Why? Mathematics and what do you get out of, if one side is four and the other side is five, and you multiply them together and you get an area of 20, what's that telling you exactly?
The size of something, how large is it? Uh, Whether it's a wall or a mirror or a garden or tiles on your floor, what's the size? An area is a measure of the size of something. And you just described a rectangle, not a square, 4 by 5, and what's the size? And then what if you went from 4 and 5, if you went up to 6 and 8? Well, then that's 48, that's bigger. So one square, if you're measuring, say, in inches, then 1 square inch, you draw that out. What's 2 square inches? What's 3? And then of course you're going to apply that to things that are not just rectangles, but you're going to apply it to all sorts of other objects, triangles, for example, and
Mhm.
trapezoids, and ultimately round things like circles. And area is just a measure of size.
Understand. Say, when we were talking before we were just, I was trying to understand math in terms of the fundamental foundations of math, and you mentioned that the foundation of math had to do with something called axioms. And I remember in geometry, which we're using as an example here, there were a number of axioms that helped you be logical about your understanding and foundation of geometry. So, what exactly is an axiom and how does it work in mathematics?
Well, what mathematics is actually is you start as a system, it's called an axiomatic system. You start out with a set of what are called undefined terms. In the case of geometry, a point is undefined, line undefined, but then the axioms are the assumptions you make about the relationships of the undefined terms. And then once you've got the axioms, then you try to prove things that will be true about them. Now, in, in a purest form, math is about undefined terms. So you can say it's about nothing. But what you do is you give these undefined terms what's called an ostensive definition. Like a point, you put a point on a piece of paper. You think of it as a
Right.
point or a point in space. And a line is a collection of points and that sort of thing. And the axioms are assumptions about them. Now, the first axiomatic system that was created by our ancestors way back in the Greek days was called Euclidean geometry.
Hmm.
And you have assumptions about points and lines, and they're called axioms. And then one of the assumptions was if you have a straight line and if you have a point outside of that line, there'll be another straight line through that point that never touches the given straight line. They call that parallel. And there'll be exactly one such straight line that does that. That's a Euclidean axiom called the parallel postulate. They also call them postulates. A postulate and an axiom means the same thing.
Right.
Okay. Our ancestors believed that that was the only geometry that made any sense. And everything they did that you take this math model and you try then to create models of real things. So in
Hmm.
Euclidean geometry, you've got rectangles and squares and triangles and circles. And they thought that was the only kind of axiomatic system you could have. And for years, a theorem now is something you can prove with a finite set of arguments, steps to get to it. So for example, in Euclid's Elements, there's 13 books, and the first book has 49 theorems in it. You prove this, then you prove this, then you prove this. And the 47th one is called the Pythagorean theorem.
Hmm.
You got a right triangle, and you show that the square of this side added to the square of this other side, you add those together, that's equal to the square of what's called the hypotenuse, which is the side opposite the 90-degree angle. That's called the
Remember that?
Pythagorean theorem.
Right.
Now, for centuries, people thought this parallel postulate should be a theorem, and they tried to prove it. They couldn't do it. Had to make an assumption. Well, then they found out in the 1800s that you could take a different geometry and change the parallel postulate instead of only one straight line that doesn't intersect the given one, you can have many. And that became a non-Euclidean geometry, completely different, just as
Hmm.
valid. They also did another one where they said through an external point, there were no parallel lines. That's another Euclidean geometry. Those geometries, when you assign ostensive definitions and try to make scientific models, became the models that were used in modern science.
So when you say prove something, for example, I learned that there were several different proofs of the Pythagorean theorem. And you just mentioned proving the um, theorem about parallel lines. So what does it mean to have a proof of
A
anything in
proof is
math?
where you start with a set of assumptions and you draw a conclusion that you can logically conclude from it. And then you draw another conclusion and then another conclusion. And so you build up to get to the proof of the Pythagorean theorem. It's proposition 47. They had to prove a whole bunch of theorems to lead up to it. Then
Mhm.
finally they could prove that theorem. So a proof is nothing more than a sequence of steps that's logical that follows from the preceding steps until you get to whatever it is you're trying to prove.
Mhm. So I understand even with the Pythagorean theorem that were different, that there were different proofs there. So not
Many,
always just one proof.
many different proofs.
Right.
To prove a given statement in math, there may be 100 different sequences to get you to that point.
Hmm.
There's no
Understand.
limit to it. In fact, I came
Right.
up with a proof. It depends on what you already know, but I came up with the proof of the Pythagorean theorem. It's only 3 steps. The one
Hmm.
in Euclid's Elements, by the way, is based on what's called a windmill diagram. It's very hard to understand, very
Hmm.
difficult. It's not in any high school books. It's too difficult. They've come up with a different way of proving it for high school books. It's easier. I came up with a proof that's only 3 lines long, and I thought, oh, wow. It turned out that was the same proof that Einstein used when he proved it.
Right. I was going to mention Einstein because he came up with a very simple proof as well. And I know that there are math students now, fortunately, because of the STEM program, where a lot more activity is going on and young people are learning how to do proofs. And I remember there are 2 young girls that recently came up with some proofs to a fairly complicated mathematical problem. And nobody believed that these 2 young girls could do it. But
Yeah,
based on
yeah. Use
but
trigonometry to prove the Pythagorean theorem. Yeah,
right, exactly. And what we're talking about, which was fantastic, to know that
sure.
young people are doing something like that.
Yeah. Oh, yeah. Yeah.
So,
Absolutely.
there really isn't any difference though between mathematics and arithmetic. Is there? I mean,
No,
when
no.
we're first
No, arithmetic is part of mathematics.
Mhm.
Mathematics, by the way, is a huge subject. Think of
Sure.
music. Think of
Hmm.
all the different music going all the way back through history, Gregorian chants, and just all the different kinds of music that there are today. Math is that complicated. There's more mathematics than any person could possibly understand. Just like you couldn't possibly understand all the music in the world. You can't even
Exactly.
listen to all the music in the world. You don't have time to. And and if you're going to learn music, you got to decide what is it you want to learn.
Mhm.
For example, suppose I told you that to learn music, before I teach you anything else, you got to learn all about Gregorian chants. Well, that might turn you off. You might say, well, I really don't like Gregorian chants, and that's the end of that. Well, they do that in math today. They teach you stuff in math that's old fashioned, obsolete, and they make you learn it. And that's why most kids today in public schools get turned off. They also bring in theory that's premature. They shouldn't bring it in. So, for example, the Pythagoreans proved that if you take the hypotenuse of a triangle that has the lengths of the 2 sides is 1, the hypotenuse, they thought that the ratio of the lengths of any 2 lines should be a rational number, like a fraction.
Hmm.
They found out that that hypotenuse, the ratio to the side, is not a rational number. And they got so upset by it, the story is they drowned the guy that discovered it, and they retreated from numbers because there's integers that you count with. That's the first thing you learn. Then you learn fractions, right? Then they have something called irrational numbers, which is a theoretical thing that no engineer or scientist cares about. And they teach that sometimes in freshman algebra books. Well, it's premature. Nobody cares. The only people that care about an irrational number are theoretical mathematicians.
And theoretical physicists, as we talked
No,
about
no,
earlier.
no, no, wrong.
No.
Theoretical physics doesn't have a thing to do with an irrational number, period.
So describe to me then what an irrational number is. An
A
example.
rational, or I'll explain it. Here's the way to explain it to you. If you take a rational number, you can always express it with a decimal expansion, right?
Hmm.
And what will happen is with a rational number, there'll be a sequence of digits that just keeps repeating that sequence over and over and over. So for
Mm-hmm.
example, for 1/3 is 0.33333 forever.
Mm-hmm.
Okay. An irrational number, when you look at its decimal expansion, never has any sequence that repeats over and over.
Mm-hmm.
That's the difference.
So why
And
would you go ahead?
no, well, that's the difference. And so
Right.
and the only numbers that a physicist cares about are rational numbers, because you always just look at you're measuring things to a few places of accuracy, and that's all. So the only numbers you ever use in engineering and in science is rational numbers.
Mm-hmm. So a particle physicist would never use a irrational number, even in quantum mechanics.
Correct. Now in quantum mechanics, you use what are called complex numbers.
Right.
Real numbers can be correspondent to points on a straight line. Okay,
Mm-hmm.
that's real numbers.
Mm-hmm.
And that includes rational numbers and irrational numbers. And
Mm-hmm.
by the way, you didn't ask me about Cantor, but Cantor is the guy that came along and proved that there's different sizes of infinite sets.
Right.
If you take the set of rational numbers
Mm-hmm.
as an infinite set, you take the set of irrational numbers, that's also an infinite set, but it's in a real well-defined way, a larger infinite set. It's a bigger infinity. And then you go up from there. Now, back to where was I? The real numbers are on a real number line. And you have positive numbers and negative numbers and fraction, and you have all the rational and irrational numbers. Now, on the plane, if you put a vertical line and put a real number line on that, they call those imaginary numbers. They're not imaginary at all. That's what they call them. And the points in the plane correspond to complex numbers. And that's critical for quantum theory.
Yeah, exactly. I know we discussed that earlier when we were discussing Roger Penrose's book, The Emperor's New Mind. In there, he used and talked about complex numbers and
And,
used complex.
a better book is called The Road to Reality.
Right, and that's a great book as well, both of which are just fantastic books that connect mathematics, to the real world and to reality, which is
So what happens is there's many axiomatic systems. In fact, there's an unlimited number. There's a finite number we've played with, but there's no limit to it. Excuse me. And mathematicians create new axiomatic systems all the time.
right.
An axiomatic system, set of undefined terms and a bunch of assumptions, axioms. And so what they do is they'll take an axiomatic system and they'll give extensive definitions to the undefined terms and create a math model for science. And Euclidean geometry was used all the way up until the starts of the 20th century. Isaac Newton, you ask about great mathematicians, all right. You had Euclid's elements, and then 200 years later came a guy named Archimedes. Now, of the three greatest mathematicians of all time were
Mhm.
considered to be Archimedes, Newton, and Gauss, Carl Friedrich Gauss.
Sure.
There's some other great ones too, though, but that's what most people think. Well, Archimedes, for example, did something that the Euclideans couldn't do. The Euclideans proved that if you take a circumference of a circle and divide it by the diameter of the circle, that is a number, and it'll be the same number no matter what is the size of the circle. And that number today is called pi,
Mm-hmm.
circumference divided by diameter. The Euclideans were able to derive the area formulas for anything with straight lines. They could not come up with an area formula for a circle. Archimedes, 200 years later, did. And today it's take circumference divided by 2 times diameter divided by 2. And then if you do a little algebra, that becomes pi r squared, which we teach kids today. Archimedes was able to prove it. It involves infinite concepts that are similar to what comes later in calculus. What he really proved then that he was proudest of, Archimedes was able to derive a formula for the volume of a sphere and the
Mm-hmm.
surface area of a sphere. And he was so proud of that, he wanted that on his tombstone. And I
No, that's
teach
what
that
it
in my practical math, Archimedes' tombstone, because I teach that in one of my programs. It's a practical thing. Now, I don't prove it. I just explain what it is. And then we went up through the, when we got to the 1600s, we had the, up until the 1600, we had the Ptolemaic model for stars and planets and that.
Mm-hmm.
And it assumed that the Earth was the center and all these things were going around it. And then Copernicus came along and said, maybe that's not right. Tycho Brahe had done a lot of observations, and Kepler was a disciple of Tycho Brahe, and he took those observations and showed that the planets go in elliptical orbit around the sun. He didn't have to have any why, that's what it does. It's an observation. Galileo touted the Copernican system that maybe the sun's the center of the universe, and he was put in jail for it. He was put in
Yes.
condemned for it. Isaac Newton, a few years later, came along with what's called Newtonian mechanics, and he assumed the law of gravity, made an assumption, and from the law of gravity, that assumption, he could derive the elliptic curves around the sun, and so Newton's mechanics then. From that point forward, we believed that the sun was the center, the planets went around it, and he wrote all that up in a book called Principia Mathematica.
Right. And what you're describing is why mathematics as a tool and as a language is so important and what you can derive and understand about reality
That's right.
from
That's correct.
from mathematics. And so that leads us to really understand what's really important about mathematics. So in your teaching and your interacting with kids, if it's in a STEM program or some other kind of program, what do you tell them as to why it's important that young people learn mathematics at all, especially if they've already been turned off from it?
Well, two reasons. Number one is I teach them, first of all, practical math that they can use so they can enter any technical field they want to. I'm not talking about engineering and science. I'm talking about a technical field, hydraulics, pneumatics, landscaping, cooking. And if you know the practical math, and I
Mhm.
teach them all that in about one semester. I teach them, first of all, how to use a scientific calculator. Do all your arithmetic with a calculator. Forget all the old manual techniques. No, they're
No
obsolete.
more slide rules?
No. You know when slide rules went out of fashion? Do you know when it went out?
Well, about when I was in college, I was still using it. And
What
so
year?
when
What year was
Texas,
that? What
that
year?
was at about 1968. So when Texas Instruments came out with the calculator,
No, the first.
that's when I
No,
stopped using it.
no, that wasn't 68. The first scientific calculator, I was teaching it in engineering school when this happened. That's how I know this. And we were teaching
Uh-huh.
them how to use slide rules and trig tables and all that. The first scientific calculator was the Hewlett Packard 35, HP 35.
Oh, yes. And when did
In,
that
to,
come out?
in today's dollars, it was $2,500,
I remember. And when,
$395 in 1972. Now, Hewlett Packard thought that they would only be bought by scientists and engineers. $395, that was a lot of money, but not for them. They thought they'd sell 10,000 of them. The first year they sold 100,000. I couldn't believe it. When I was teaching engineering school, some of the children there, some of the students were well-to-do, came from rich families, and so they had the calculator. We weren't teaching it. I asked one of my students, what is that thing you got there? And he says, it's a new calculator. He showed it to me, and I played with it for about 30 minutes. I go, oh my God, slide rules are obsolete. And they were. And because the calculator now does all the calculations much quicker than log tables and trig tables and slide rules, which is what a slide rule is. It's just a set of log tables, really. And so then Texas Instrument came out with better calculators at a lower price. And so the price went from $395 down to $195. And then Texas Instrument came out with a better calculator under $100. And that kept going. And today,
well, that's what I used.
the TI-30XA is what I tell people to use. It's a $10
Mhm.
calculator today. Remember, 2,500 down to 10, and this is a better calculator. Now, what happened in the 90s was they developed graphing calculators, and that was state of the art in the 1990s. As of 2009, all graphing calculators are obsolete. Why? Wolfram Alpha is the new tool that came out in 2009. It's free, and it does all of the math way more than the graphing calculators does. It solves all calculus and differential equations and all that kind of thing, which calculators don't. And so what I teach is the first thing is I teach the practical algebra, geometry, and trig with that calculator. And that takes most students about less than a year, one semester usually.
Mm-hmm.
They're now ready for the military. They're ready for a technical career. If they don't need to go to college to do that. You can go get in a technical career, make $40, $50 an hour, take you 2 or 3 years to learn the technology, but the calculator makes it, and the practical math that I teach you makes it easy to do. Want to go to college, in Tier 3, I teach them the math you need for the SAT and the ACT. Horrible tests, but you might have to take them. Mm-hmm. And again, and I won't get into the details of it now. You can go to my website and learn all about it, look at the syllabus. Then if you want to go into science engineering, you want to go much deeper into math. And at that point, I start using Wolfram Alpha, and that makes learning math for science and engineering from a difficulty level of 8 down to 2. Mm-hmm. It makes calculus easy.
In what way? In what way does it make it easier? I mean, you still have to have an understanding, a basic understanding,
all right,
and knowledge of it.
That's correct. There's two parts in math. There's the concepts, and mm-hmm. there's the tools to apply the concepts to solve problems.
Okay, that's what I'm getting at.
Now, mm-hmm. the concepts are easy. It's the old manual tools that are very difficult. Mm-hmm. For example, if you want to take the square root of a number, I'll just use an arithmetic example. If I give you the square, well, let's just take multiplication. What is 369 times 87? Bingo, 32,103. Now, if you did it the old manual way, how long would it take you with pencil and paper?
It'd take me forever.
Well, no, but it'd take a long time.
It'd take a long time, of course. I'm exaggerating.
What's the square root of 3203? There's a manual tool that I used to teach students to use, an old manual tool. Or later on, then there's an algorithm to do it. Or later on, there was slide rules. But today, bingo, the answer is 179.2. Mm-hmm. Now, when you get into calculus, the problem with calculus is you're studying what are called functions, and you want to know the maximum, the minimum, the points of inflection. That's called differential calculus. And to do that, you have to take derivatives of the function, which isn't too terribly difficult, but then you got to analyze what are the 0 points of the derivatives, and that's very difficult. Wolfram Alpha does it. Bingo, bango, done.
But when somebody, but if you're learning mathematics and you're in calculus class and they're in your calculus class and you just said what you said, you have to take the derivative. And I remember when I was first learning this, I was like, what? What is a derivative? So how do
you teach the concept. When I teach calculus in my program, which is mm-hmm. Tier 5, I teach the concept. The concept of derivative is actually easy.
And it is.
You got a function. Mm-hmm. You take a graph of a function. You take a point on the graph, and all the derivative at that point is the slope of the tangent line. Mm-hmm. And there's a way to calculate it using what are called infinitesimals, very quick and easy. In fact, you can even calculate it with this calculator, and I teach you how to do that for that one point. Now, if you want it for all the points, that's called the derivative function. You got to calculate it for all the points, and that would be very time consuming. So then there's techniques now, manual techniques, to make that a little bit easier, but it's still quite difficult. Wolfram Alpha does it for you. So the concept is easy. Now, the other thing about this, that's differential calculus. Integral calculus, you've got a graph of a function, okay? Here's a graph of a function. You want to know the area from point A to point B underneath that graph. Mm-hmm. To do that, you have to apply the fundamental theorem of calculus discovered by Newton and Leibniz back in the 1600s. which
Hmm.
is why we have modern science. The fundamental theorem of calculus, most important theorem in the history of mathematics, because all modern science grew out of that. Up until then, they didn't know how to do this problem. Okay, you take the function and you've got to find another function whose derivative is the given one. That other function is called the antiderivative. That's very difficult. That, and often it's impossible. And so that is what flunks more kids out of engineering school than any other thing. It is
Hmm.
so difficult to learn and master. And Wolfram Alpha does it for you automatically.
Hmm. Hmm.
So the concepts are easy. It's the old manual tools that are extremely difficult.
Hmm. To get
So,
the answer that you want.
and then the workhorse of science, and this is never taught in high school now because it's way beyond, are called differential equations. And a differential equation is an equation whose solution is a function. And
Hmm.
finding that solution, you mentioned Einstein earlier in an email to me, finding the solution to the differential equation can be extremely difficult. In
Hmm.
fact, in some cases, impossible to do with any ordinary functions. Wolfram Alpha does it for you automatically.
So I did mention to you earlier that I was going to ask you a question about solutions to problems. So you have all of the differential equations that are part of Einstein's theory of general relativity, and there was a solution that predicted the existence of black holes.
That solution was
So,
based on, no, that was based on certain assumptions.
okay, so
In
explain.
addition to, well, Einstein came up, they're more than differential equations. They're more complicated than that, but he came up with a mathematical
Right.
model.
Hmm.
Okay. Now that mathematical model can have solutions, but they couldn't find them. So what happened was Schwarzschild, he made some assumptions added
Schwarzschild.
to that model, and then with those assumptions, he could derive a quote solution. And that happens all the time in math. You make assumptions so you can derive a solution. And uh, the thing today that's interesting in theoretical physics you mentioned, back in the late 1970s and early 80s, they started coming up with new axiomatic systems, very complicated to understand, and applying them to physics, and it became a subject known as string theory.
Hmm.
And string theory has all these fabulous mathematical models, very complicated, extremely complex. I don't understand them. I haven't studied them. And the problem they got is they can't come up with any predictions that they can actually test in the real world.
Right.
And so string theory is effectively a failed attempt to come up with a mathematical model, a physics model to explain what's happening. Because
Right.
here's a problem you got. You got a set of equations for relativity theory, Einstein's equations, okay?
Hmm.
You got a different mathematical model for quantum theory.
Hmm.
They
Sure.
contradict each other.
Sure. Understand.
They contradict each other. Now, if you're looking at things that are astronomical, you use Einstein's theory. If you're looking at things that are like down at the proton level, you use quantum theory. And then you try to look at something where they overlap and they contradict each other. It's a problem today they have, and they don't know what to do about it. And then on top of that, they've now discovered, and this goes beyond now math, they've discovered empirically that there is something they call dark matter, and they have no idea what it is. They have something else they call dark energy. They don't know what that is. And so today, our theoretical science today is in a heck of a quandary.
Hmm.
Yeah, we know a lot. We've learned a lot, but there's a lot we don't know. And it's just,
Well, yeah, and I would like to refer our listeners to my podcast, The Crisis in Physics. We did a whole podcast on that a couple of years ago
mhm.
with the scientists from Europe, where we talked about these kinds of issues. But
Yeah.
let's pivot and talk a little bit about some of the fun things in mathematics, and some of them are related to prizes and they're puzzles. And I love mathematics puzzles, but some of them are really complicated and it's difficult to find answers. And one of the things that my son and I have fun discussing, and I will, of course, never come up with a solution to this, but it's the twin primes problem.
Well, that's not one of them. That
not
is a
one of what?
conjecture. The
I'm
Clay
sorry.
Institute, the Clay Institute has
Mm-hmm.
got 7 problems for $1 million.
Mm-hmm.
The only one's been solved so far, the Poincare conjecture.
Right.
A Russian solved that, and by the way, he turned down $1 million. There's lots of conjectures out there. The twin prime conjecture is not one of them uh, that they'll give you the money for, although they probably would. If you could prove it, you would become very famous. And uh, okay, do you want you want to talk about that or?
Yeah, I just wanted you to describe for our listeners what that is. A lot of people hear that talked about, and it's even talked about amongst my listeners. And I just
Yeah,
wanted to take a minute and talk about what
yeah,
that.
it's one you can understand. The
Hmm.
7 that they'll pay you money for are so complicated that you wouldn't understand them. I don't understand most of them. They're just too much
Right.
theory. Uh, a prime number, you have integers, 1, 2, 3, 4, 5. A prime number is one where the only divisors are the integer and itself. Like 3 is a prime number. 6 is not a prime number because you can divide it by 3 and by 2. 7 is a prime number. 8's not. 9's not, and so forth. Now, they proved a long time ago that there's an infinite number of prime numbers. No matter how far you go, there's always more prime numbers. They proved that a long time ago. Then there's twin primes. For example, 11 and 13 are twin primes. 11 is a prime, 13. Twin prime means they're right next to each other with one even number in between them. 17 and 19, and so on.
Hmm.
And the question is there a limit to it? And so I went earlier today and I went on to Google twin prime conjecture. How many twin prime? Uh, I looked earlier. How many twin primes were there um, that they found? It was kind of interesting. How many twin primes under 10 million? Okay. Oh, okay. 10 million, the answer here written out is 58,980. Under 100 million, there's 440,000. The point is there an infinite number of them? Now, infinity is what I call the black hole of mathematics. The minute you didn't ask about Cantor. Cantor was one of the most profound mathematicians of the 19th century.
Yeah, one of my
And,
favorites. I appreciate it.
and he's the guy that came up with the factor of different sizes of infinity.
Hmm.
And no matter how big an infinite set is, there's another infinite set that's even larger and under a good definition, and you just keep going. So the infinite number of infinite sets. Now, this is all theory. This is not practical.
Hmm.
This is not real world stuff. In fact, when you get into theoretical math, you start using infinity, you get a lot of things that are very unintuitive. I'm going to give you an example. Take all the numbers between 0 and 1. There's fractions they call rational numbers, and there's irrational numbers. I
Hmm.
told you earlier what that is. That's numbers that don't have any
Hmm.
repeating in their infinite expansion. Okay. In between every 2 rationals is a bunch of irrationals. In between every 2 irrationals, a bunch of rationals. So they're all dense between
Hmm.
0 and 1. Now, here's my question to you. If you reach in at random and pull out a number between 0 and 1, what is the probability that will be a rational number?
Hmm.
What do you
It
think?
seems, I don't know. I mean, it seems to be infinite. I mean, there's so
The
many
probability has to be between 0 and 1.
0 and
What's the
1. Well,
probability that you'll pick out a rational number if you just pick
I
out an
don't know.
arbitrary one?
What's the
I know you
answer?
don't know, but take a guess. Ask your readers, ask your listeners, take a guess. What do you think would be the probability you get? There's rationals and irrationals, and they're intermingled densely. You reach in, you grab one at random. What is the probability you'll get a rational number?
I'll ask my listeners.
What do you think?
So the probability between 0 and 1, and I have to give you a number between 0 and 1 of the
Yeah,
probability of
all
finding,
probabilities are between 0 and 1.
I don't know, almost zero.
Well, it is actually 0. Most people guess a half
I said almost
because
zero.
you think,
So.
well, they're all intermingled. But the facts are the rational numbers are what is called countable and the irrational are uncountable. And if you look at measure theory, the way it's defined, the probability of getting a rational number is zero. Now that's theoretical math. Any theoretical mathematician knows that, but
Hmm.
that's very non-intuitive.
Right.
Theoretical math is extremely non-intuitive. For example, when you do measure theory, if you take a non-measurable set, you can take a sphere the size of a grapefruit and divide it into a finite number of parts and put it back together and be the size of the sun. Now that's crazy. You say that's not, well, it is. It's theoretical.
Right.
Theoretical math is quite something. It's
Right.
but then they take math and they make math models out of it for science.
Right. Well, it's even come up in religion. You mentioned Cantor, and I don't know if you're familiar with the book, The Mystery of the Aleph, and I can't remember the author's name.
I'm
Anyway,
not.
he went insane
Yes, he did.
because I'm sorry,
Yes, he did.
because he was trying to um, understand God in terms of mathematics and in terms of going back to the Jewish concept of the mystery of the leaf. The Aleph is a Jewish letter. Um, and what he was trying to do was get to this understanding of a wheel within the middle of a wheel. And he worked diligently to try to, using set theory, to try to understand if he could find God within, this mathematics, and it ultimately drove him crazy. I don't know if you read the book, but
No, I haven't read the book. I didn't even
it
know that
was
story. I know
it
he went
was
crazy because he was very, when he came up with his concepts of infinity,
mhm,
Cantor's diagonal methods and proving that the irrational numbers are non-denumerable, he was severely criticized by a lot of his fellow mathematicians.
mhm.
And what I've read is that they basically drove him crazy. Now, one of these other reasons you just mentioned, I don't know anything about. It's not
Yeah,
mathematics.
yeah, you'd have to read the book. Well, there's a lot of mathematics in the book too. The Mystery of the Leaf. I'll send you a reference. I think you'd really be interested in
Well,
it.
I might be. Yeah, sure, sure,
It's fascinating.
sure.
So the last question is we wrap this up, and it's a good place to wrap up. Is that we discussed earlier when we were chatting Gödel's incompleteness theorem, and maybe you could take a second and talk about what that means, because I think there are a lot of misconceptions. I mean, for example, people says, well, it means you can't know anything, or it means that, mathematics can't really teach us anything because
No,
we
that's all
can't really know
nonsense.
anything.
No, that's all
So
nonsense.
it's kind of all over the board. So why don't you spend a minute, and I think you did it quite eloquently and simply the last time we spoke, explaining what Gödel's
Well, I'll
incompleteness
try to
theory
make it complicated this time. Here's the deal.
is.
Kurt Gödel in the early 30s came up with this. If you have an axiomatic system that's complicated enough to contain the natural number system, okay? And that's most mathematical systems are that complicated. Then there will be statements within that system. First of all, a theorem is a statement that you can prove with a finite set of steps reasoning using logical steps to get to prove it. That's a theorem you can prove. He showed that there would be statements within that system that are true, but there is no finite set of steps to prove it.
Mhm. That was the simple explanation you gave, and I think the problem is that people interpret that different ways, and
Well, people, yeah, that it, and the question is, for example, you mentioned the millennium problems. The most famous one of those is the Riemann hypothesis.
Mhm,
The Riemann hypothesis was Bernhard Riemann. He came out with it in the 1800s, 1859, I think. If it's true, it tells you something about the distribution of prime numbers that otherwise we don't know. And a lot of people think it's probably true, but we can't prove it. And
mhm,
the question is it something that maybe can't be proven? Could it be one of these Gödel? Nobody knows. We
mhm.
can't prove it. They've been trying to prove it for 150 years. And if of all the 7 millennia problems that they would give you $1 million for, that's probably considered the most challenging and most difficult.
Would you describe that again so my listeners understand what that problem is? Because it's a beautiful problem.
All these millennium problems are extremely difficult to understand if you don't know theoretical math. But the bottom line of it is, it's hard to explain the Riemann hypothesis. The bottom line of it is, it involves a function of complex numbers that Riemann created, that a mathematician would understand, and that function has what are called non-trivial zeros, where they have to lie between the vertical line above 1 and the vertical line above 0 in that line. And he hypothesized that they would all lie on the midline, where the real number is 1/2. That was his hypothesis. And if that's true, a lot of things follow from it about the distribution of prime numbers. Nobody can prove it.
Mm-hmm.
And they've calculated it up to, I don't know, trillions, but that doesn't mean anything. Infinity is so much larger than any finite number that it doesn't mean anything.
Sure.
You can know something is true to trillions and trillions and trillions, but that doesn't prove it's true for everything. And so it's just like the twin prime conjecture.
Well, Craig, where do you think mathematics is going in the future? I mean, if you were a science fiction writer talking about mathematics and you were going to predict something that we're not even thinking of today, where do you think math is headed? I know it's kind of a theoretical question.
Two things.
Mm-hmm.
One is, there will be more axiomatic systems. You can choose a set of assumptions called axioms, and then that's a math system. There's an unlimited number of those, and we've only done a few of them. So there'll be new axiomatic systems, and then those systems will be used to create scientific models. They're trying to do that now. That's what string theory is trying to do,
Yes,
to
string
unify
theory.
quantum theory and relativity theory, and they have failed so far.
Right.
So there'll be new axiomatic systems, and within any given axiomatic system, there'll be new theorems proven. Maybe they'll prove the Riemann hypothesis. Who the hell knows? And that will go on as long as we are growing as a species and surviving. That'll continue on. Now, the new tools today are helping us do more because they can do calculations that lead to ideas that we might be able to go beyond. And we don't know what AI is going to do for us yet. Artificial intelligence, they call it. We don't know. AI today, this is not just mathematics now, this is really engineering and science, is transforming the world we live in.
Mm-hmm.
They don't even understand how the damn thing works. They don't know how these large learning models work. They put together, ChatGPT. You're familiar with ChatGPT, probably.
Yeah, we just did two. In fact, we did 2 podcasts on that, and just the one before, 2 or 3 podcasts before this one was all about AI. For our
And
listeners, you can
these
go
large
back and
learning
listen to those
models are
too.
getting,
Mm-hmm.
they keep adding to them and changing them, and they keep doing more stuff. They don't know how they work.
Yeah.
They don't know.
Well,
In fact,
it's
they're
going to
doing
be
things that they didn't anticipate.
right. It's going to be a fascinating future. Well, Craig, it's been a pleasure chatting with you. Really
Let me
appreciate it.
let
What's
me
one
say
of the
this.
last things you'd like to say?
Okay,
Go
what I
ahead.
like to say, I put together a thing called the Triad Math Tribe,
Uh-huh.
and it has not only the 6 tiers of math that I teach, it also has a whole collection of what I call wisdom tools. I've had a lot of people come to me and say, Craig, you've had this fantastic life. You're 86 years old. You're healthy, blah, blah. You've done all these things. I said, I was very blessed to get these wisdom tools from all sorts of sources that help me do what I've done in life. And people say, well, can you share those with me? So the answer is yes. I've got a whole list of wisdom tools. Now, what you can do is you can go to my website, craighane.com,
Mm-hmm.
CRAIGHANE.com. Click on the link that says improve your life, and that will take you to a web page. And for $9, you can have access to everything for a whole 30 days. And then you put your time into it, it ought to be worth God knows how much for him.
Mhm. Well, that's great. And I'll certainly put that in the show notes as well, and on the website, because you'll be on our website as well. And I'll mention it
Wonderful.
again.
Wonderful.
Thank you. Thank you for
Thank you.
joining me, Craig, on
Th-
Nature and Science podcast. We really appreciate it. This was a fascinating discussion.
Thank you, Don. I really enjoyed it. Keep up the good work.
Hey everyone, thank you for listening to this episode of Nature and Science Podcast. We appreciate your support. Please subscribe to our podcast at natureandsciencepodcast.com, and don't forget to hit that like button. And by the way, science does care what you think, so leave us a comment. As always, stay safe, share happiness, and remember, never stop questioning. Curiosity has its own reason for existing.